Welcome to this lesson on the Wald test. In this video, we'll see how an estimated parameter is transformed into a test statistic and how that statistic is used for hypothesis testing. By the end of this video, you'll understand what the Wald test is, how to construct its test statistic from an estimated parameter, why it is approximately standard normal for large samples, how to apply it to a Bernoulli parameter, and how to make a hypothesis testing decision. A natural question is, where does a test statistic come from? In classical statistics, there are three widely used hypothesis tests: the Wald test, the likelihood ratio test, and the score test. Although they are developed differently, they are asymptotically equivalent under suitable conditions. Today, we'll focus on the Wald test and see how it is constructed from an estimated parameter. Now let's construct the Wald statistic. Suppose we want to test a hypothesis about an unknown parameter, theta. Here, theta naught is the value specified by the null hypothesis, and theta hat is our estimate of the unknown parameter. The Wald statistic compares these two values. It measures how far the estimate is from the hypothesized value relative to its estimated variability. The denominator is the estimated standard deviation of the estimator. We estimate the variance of theta hat and then take its square root to obtain the standard error. Many textbooks and statistical software packages simply write the denominator as the standard error of theta hat. Therefore, the Wald statistic can be written as the difference between theta hat and theta naught divided by the standard error of theta hat. This is the form of the Wald statistic that we'll use throughout the rest of this presentation. Suppose theta hat is an estimator of the unknown parameter theta. Under the null hypothesis, theta equals theta naught. For large sample sizes, we standardize the difference between the estimator and the hypothesized value by dividing it by its estimated standard error. The resulting standardized quantity is the Wald statistic. Mathematically, we write this as W converges in distribution to a standard normal distribution. The symbol D above the arrow means converges in distribution. In practice, this simply means that for sufficiently large sample sizes, the Wald statistic is approximately standard normal. This asymptotic normality is the key idea behind the Wald test. It allows us to compare the Wald statistic with critical values from the standard normal distribution and make statistical decisions. Let's illustrate the Wald test using a Bernoulli distribution. Suppose each observation is either a success or a failure. We record a success as 1 and a failure as 0, so a sample might look like 1, 0, 1, 1, 0, 1, and so on. The probability of success is p. The estimator of p is the sample proportion, p hat, which is simply the proportion of successes observed in the sample. The variance of this estimator depends on the true parameter p. However, because the true value of p is unknown, we cannot calculate this variance directly. Instead, we replace p with its estimate, p hat, to obtain an estimated variance. Taking the square root of the estimated variance gives the estimated standard error of p hat. This estimated standard error appears in the denominator of the Wald statistic and is used to standardize the estimator. Now let's apply the Wald test to a Bernoulli parameter. Our null hypothesis states that the population proportion is equal to p naught, while the alternative hypothesis states that the proportion is different from p naught. The Wald statistic is obtained by taking the difference between the estimated proportion and the hypothesized proportion, then dividing by the estimated standard error. For a Bernoulli distribution, the estimated standard error is obtained by replacing the unknown parameter with its estimate, p hat. Substituting this estimated standard error into the Wald statistic gives the expression shown here. Finally, under the null hypothesis, and for large sample sizes, the Wald statistic is approximately standard normal. This result allows us to use the standard normal distribution to perform hypothesis testing. Let's work through a numerical example. Suppose a health agency claims that 50% of people develop immunity after receiving a vaccine. This is our null hypothesis. We randomly select 100 vaccinated people. Among them, 60 develop immunity and 40 do not. The estimated proportion, or p hat, is 60 divided by 100, which equals 0.60. Next, we calculate the estimated standard error using the Bernoulli standard error formula. Substituting p hat equals 0.60 and n equals 100, we obtain an estimated standard error of approximately 0.049. Finally, we compute the Wald statistic by subtracting the hypothesized proportion, 0.50, from the estimated proportion, 0.60, and dividing by the estimated standard error of 0.049. This gives a Wald statistic of approximately 2.04. In the next slide, we'll compare this value with the critical values from the standard normal distribution to decide whether we reject the null hypothesis. We are now ready to make our statistical decision. Under the null hypothesis and for large samples, the Wald statistic is approximately standard normal. Therefore, we use the standard normal distribution to determine the critical values for our hypothesis test. We choose a significance level, denoted by alpha, equal to 0.05 or 5%. Because this is a two-sided test, we divide the significance level equally between the two tails of the standard normal distribution. As a result, each tail contains 2.5% of the total probability. The corresponding critical values are minus 1.96 and plus 1.96. These critical values define the shaded rejection regions in the two tails of the standard normal distribution. Our decision rule is simple. We reject the null hypothesis if the absolute value of the Wald statistic is greater than 1.96. From the previous slide, we calculated a Wald statistic of 2.04. Since the absolute value of 2.04 is greater than 1.96, the observed Wald statistic falls in the right rejection region, as indicated by the red line on the graph. Therefore, we reject the null hypothesis at the 5% significance level. We conclude that there is sufficient statistical evidence that the true immunity rate is different from 50%. Let's summarize the key ideas from this lecture. The Wald test compares an estimated parameter with its hypothesized value. It then standardizes the difference by dividing it by the estimated standard error. This allows us to measure how far the estimate is from the hypothesized value in units of standard error. Under the null hypothesis, and for large samples, the Wald statistic is approximately standard normal. Therefore, for a 5% two-sided test, we reject the null hypothesis whenever the absolute value of the Wald statistic is greater than 1.96. Finally, you may notice that some textbooks and statistical software report the squared Wald statistic instead. Under the null hypothesis, this statistic follows approximately a chi-squared distribution with 1 degree of freedom. For a single parameter, it is mathematically equivalent to the standard normal form that we used throughout this lecture. Thank you for watching.